For TI questions, the first one is components and types of intelligent systems. Components, the components mainly are you have a host, you have a storage network, then you have a front end, cache, back end, and physical device. Front end has ports which are connected over here, so you use a port over here. That is, these two are the controllers. And these are the ports which connect to your controllers. Okay, so what happens here is your front end processes the input request uh, from the host. Your cache, it saves all the data which is got, and then the request that is sent back. And then you have the backend and the physical device. Physical device is where you store your data, your main memory data, and how you collect it from there. And then your backend is the way from cache to your main memory storage. So all this is integrated on a single board. So you write everything. You write about everything, whatever you know, that there are two controllers. There are four ports, which each controller has two ports. And then you write about how the front end uses internal ports to get the data from the cache. And then you write about how the one once the data is given to the cache, your front end sends an acknowledgement to the host via the storage network. You have second question, that is read and write cache operations. So write a little bit about cache, like it is the temporary storage, and then it helps in performance and all, and then it helps to deliver data faster. And then you write about read operation. Okay, what happens in read operation is you have a host, you have cache, and then you have your physical disks. So what happens is first the host requests the data, then the request is read by the cache and to the physical device. It gets the data from the physical device, that is 3. Your cache gets the data, and the data is given back to the host is in 4. Okay, so what you're doing is you write this in your own words. Okay, you write if the read cache, if it gets the data, it's a cache hit if the data is there in the cache. Otherwise it's a cache miss. Okay, so that is the data is not there in the cache data. What you're doing is you're going ahead and then fetching data. If you see normally, only what happens is if it is there in the cache, only the request is sent, you find the data over here, and then you send the data back, right? So that is when your cache hit happens. When a cache miss happens, the data is not there and it has to go there, go further. So this is called prefetch or read ahead. That is, you draw this diagram for writing about cache miss and cache hit. That is, if you're this thing, if it is a miss, you write this. If it is a hit, you write this. Okay, you write this diagram. That is, one, it requests data, and then it just sends the data back. You don't have any connection over here. You just have to draw one straight line. And then you have that prefetch and read ahead. No, those are algorithms that are used sequentially to have sequential requests, so that it can get the blocks of data and then keep them ready, so in the physical disk, so that it can be sent back to the cache. Okay, so what you're doing is you have in all this prefetch and all, you're having fixed size variables and then variable size variables, so that you'll send the blocks of data, right? So it can either be fixed or variable in size. That is what you're writing about. The same thing about write. What happens in write is that same two diagrams. For writing also, it is for writing you don't have any data. Okay, what happens is it sequentially writes the data. Okay, you have a write back option, that is your device to your cache to your host. Okay, so whatever the content is placed over here, if it is repeatedly accessed, you place this to the host, and then this thing can be written, it will be accessed by the host later on. So write through cache, this is a write back cache. That is, you don't usually involve your cache in this. Sorry, write back cache is when your data is placed in your cache, and then you give acknowledgement to the host. It's not that you're sending it to the host. Once your host will ask you to write something into the cache, you'll write it into the cache, and then you'll send acknowledgement to your host saying that it has been successfully written. Then you're writing through cache. So what is happening here is that you're writing to the disk, and so you're writing it directly to the disk. Okay, so you're not writing it in cache First you're writing it, what happens here is you're writing it in cache in write back. First you write it in cache and then you send off the acknowledgement to your host, okay, and then it'll slowly upload the data whenever it has time. Right through caches, it'll send it through your cache and then immediately write it off into your disk, and then you're making sure that the disk is arrived, okay, and then you get your acknowledgement also almost immediately. Then you have rate techniques with suitable diagrams. While doing the first question, I only explained the components of intelligent storage system, right? So here the types are there. That is, you have high end and then mid ranged. Okay, so high end, what happens is you have both active, and then in mid range it is passive active. What happens here is that you have your host and then you have your front end part of the device which is connected, that is your storage access. You have two controllers, and in this one will be active and one will be passive, or both will be active. This is what active or active passive means, okay. So this storage actor access over here is the LUN, okay. The LUN means the storage access. So what happens here is that in the first one, that is in your high range, your active, you have a few these things, okay, that it can store large capacities of data. These are your advantages. It can store large capacities of data. It can have a huge amount of service hosts for IO to be it can be more optimal, okay. And then you have fault tolerance. So that means you have a lot of availability. And then you have connectivity to mainframe computers, and then you have a lot of multiple front end ports, so you can have a lot of number of hosts which connect to it. So other than this, you have it is scalable. Yeah, so if it is scalable, then you have better performance and all, and your capacity is like you have a lot of capacity requirements. So it has ability to handle different. I mean, it can fix 4 or 5 input output devices, and then it can handle all of them well. And then it supports any form of array based local or remote replication, okay. So you can have data which you can replicate remotely or directly. So that is with your large end storage type. And then you have your the same thing for mid range. What you do is here is instead of active, you'll have active and passive, okay. Same thing, you have a front end, you have two controllers, you have ports, and then you have storage access, and this is an LUN which is connected, okay. So what is this is, it is used for large size companies. This is used for medium size companies. It is low cost, and only owning controller of only the active one can perform tasks. That is, in your active path, only output can perform tasks, and only few front end ports can be input output ports can be connected. And then you know that you have higher redundancy, and then performance application is predictable. And this is also similar, okay. They support array based local or remote replication of data. So 1 and 2 done. Then suitable rate techniques. So in rate based technique, they mainly talk about 3 things, okay. Parity, mirroring, and stripping. Stripping happens. What is stripping is, you're splitting the data in parallel. You have one large chunk of data, so then 4 or 5 data applications will be split in parallel, okay. And then the usage is predefined, and then you can continuously it can be continuously addressed. So what you're doing is, you have first server, second server, third server storage, and then you're just splitting the data. You're writing it into different parts of the disk. You'll have 3-4 disks, and then you can write it together. That is stripping of data, okay. And then what happens in mirroring is, you make an additional copy. So if you have ABC as one set, and then you'll have ABC in the other set also. So what your advantage is, redundant, faster recovery. So you have all your data being mirrored, right? So you have faster recovery, and data protection is present. So what happens is, even if your whole thing fails, disk fails, you can use the thing from this disk. But what happens is you can't frequently take backup. So if you're editing after this, if you add ef or something, it will not be mirrored. So you need to mirror the whole thing at once. So duplication space and what are the disadvantages? You have to use duplicate space. So you need one whole space for this only, right? So you're not just storing partial value, you're storing the whole value. So you'll need two spaces instead of using one. So and then the other one is it's expensive. Parity, I'll tell you. You have parity, and then this is a method used to protect stripped data from disk drive failure without mirroring it. Mirroring uses a lot of extra disks, right? So instead of doing that, you use a parity. That is, you have a redundancy technique, okay? So instead of copying all the data together, you're just taking one bit from each storage, and then you're just making one extra backup device, okay? So this is your parity bit. So your calculation of parity is done by RAID controllers, like how much parity you have to give, how many disks you need to allocate, what and all should be transferred as this thing. Okay, so it's a redundancy technique, and then your parity calculation is done by XOR. Okay, I mean the bitwise XOR. Then you have the question about comparison of all RAID levels. So what you have to do is basic RAID levels, I'll tell you. Comparison, you have to see the table, and then see the table once, you'll understand. And then you have stripped data set, and then no tolerance. In R0, that is, you have stripped data, no tolerance. R1 is disk mirroring, so the whole thing is mirrored. Nested is R0 plus R1 or R1 plus R0. That depends. And then you have stripped data set, which happens in so in R3, the stripped set is written across in a parallel format, and then it has a dedicated parity bit. And then in R4, you have stripped data plus written in parallel, but it has an independent parity thing. And then for this, you don't actually have a diagram, no diagram. And then in R5, you have a stripped, and then it has a distributed parity check. Stripped, parallelly written, and then distributed parity. You have stripped and parallelly written, and then you have dual dedicated parity. This means that you'll have not just one copy, you'll have two copies in dedicated parity. And then you have distributed parity. In that, you'll have in every disk, you'll have one copy of your parity bit that must be present. And then you just have to explain about FC SAN, and then nodes, their ports, connectors, interconnecting devices. So your components of FC SAN are, first you see what is FC SAN. That is your fiber channel SAN. Now this is, a fiber channel is nothing but high speed network that runs on optical cables preferably, and then or serial copper wires. In this FC technology was created to meet the demands of you needed faster data, so that's why you created FC SAN. Okay, then the components are node ports, cabling, connectors, interconnecting devices such as FC switch or hubs, and then SAN management software. In node ports, what happens is you have a fiber channel, and then you have in a node you have like tape libraries that are referred. So all this, see, when you're connecting a device over here, you have in topology, you know, when you connect, you have this is called a node, right? Like you connect devices over there. So this is it's a source or destination. It's either a source for information to go, and then or it's a destination. So it's like a point. And then each node requires one or more port to provide physical interface for communication. A port is a full duplex data transmission mode with transmit TX link and a receiver link, that is RX link. If you remember from IoT, you have TX and RX in that Arduino board, right? So it's like that. Then you have nodes over here, that is port 0, port 1 up to port n, and each port has like a link. One is a transmitter link, and then one you have a receiver link. Then you have cabling. You have cabling that is done. So it uses optic fiber cabling, right? And then you have copper that can be used for long distances, I mean for shorter distances, because it is of it has a smaller area, so it is copper can be used for shorter distances and connectivity. Optic fibers can be used for long forms of connectivity. And then you have mainly two modes, that is multi-mode and single mode. Multi-mode, what happens is your Your data is carried in different lengths. Wait, I'll just show you the diagram. The reason why we were using copper is that it has a signal noise of 30 meters. Okay, you can't use it for more than 30 meters. That's what multi-mode optic fiber cables and then single mode optic fiber cables. Here, multiple beams of light can be projected. That is in multi-mode you have multiple beams of light which is projected at different angles of different bandwidths. That is 6.2. That's what you have, OM1, OM2, OM3. Okay, this is optic mode 1, optic mode 2, optic mode 3. These two are of the same micrometers, and then this is of 62.5 micrometers. So that's your bandwidth. Collision weakens the signal, and then modal dispersion is reduced. So your modal dispersion is the amount of data that can be transferred. So for smaller distances, if you have a smaller if you have a smaller core, then what happens is your signal gets degraded. Okay, so this is called annotation. In single what happens is In single mode what happens is you have a single light which is projected at the center of the cone, then which is of 7 to 11 microns, or in generally it is 9 microns. So what happens is here is that you have a minimum number of signal annotations because it is being sent in a straight line. So here what happens is light goes in different angles, and then here light goes in a straight line. So here you have data sensors, that is HT, and then you have connector cables. This is your ports. Connectors, these are your this enable connection to the cable. Okay, so you have a standard connector, that is your these are the plugs which you connect to your computers, bro. Okay, and then you have a lutent connector, that is LC. That is, you have a smaller pins over here, and then these are the two most common optic fiber cable. So in SC what happens is you can your transmission speed is up to 1 gigabyte, whereas in LC, that is your lucent connector, you have up to 4 GB per second. Okay, so these two are this thing, and then you have a straight tip connector which is used nowadays. Okay, which looks like a plug and a socket that is locked with a half twisted bay knot. Interconnection devices, these are your hubs, switches, and directors. Hubs are used for these are communication devices which are used for used in fiber channel FCAL implementations. These hubs are physically connected to a logical loop. Okay, so that it's like you're creating a connection device which can be sent to multiple nodes later on. So it's like you're creating a topology. Okay, so what happens here is that because of availability of low cost and high performance switches and switches, hubs are no longer used in SAN. Switches are more cost effective, so they use switch now. So switches are more intelligent than hub, and then they directly route data from one physical port to another. So therefore, nodes do not share the bandwidth. Instead, each node has a dedicated communication path. So here what happens in hub is you have one hub, and then it goes to a common thing, and then it decides which one it sends it to the data is sent to every node, and whichever node actually had requested for the data, it gets selected there. In switches what happens is that you have a dedicated server, only one of them gets the content, the one which had the host which had asked the data gets the data. And then same thing with the switches are available with fixed port count, and then modular design. So how many open slots, and then you can have additional port cards that can be installed. Then you have directors. These are little larger than switches, and then they're used in data center implementation. So you use it for a much more larger. If you have a data center, you use it for that. And then you have function. This similar function to FC switches, but the directors have higher port count, so you have a lot of ports, and then fault tolerant capabilities are present. It also has port card or blades of multiple ports for connecting other FC switches. You can also have it connecting to multiple FC switches. So then you have last part is SAN management software. Here you have a management software which acts as an interface between hosts and interconnected devices and storage array. So using it's like a net storage software. This software provides a view of the SAN environment and then enables management, okay, of various consoles. It provides key management functions including mapping of storage devices and then servers. It gives you like how the functions can be done, and then it is what you're allowed to discover devices, and then partitioning of SAN happens, which is called as zoning. You have a SAN, right? You can divide it into multiple parts, and then you're zoning it. Okay, so you have zone A, that is only for display, zone B, which is only for servers, and then zone C, which is only for storage, things like that. So these are all and then these, if you see your read in detail of that table, you'll have a table for comparison. If you see that, it'll be there.